So, um, okay. So the shortest explanation when people talk about recursion is this idea that recursion occurs when a function calls itself, and it's a little bit of an oversimplification. And in some ways, when you say it like that, it almost begs the question of, okay, well, why not use another format, right? Like a while loop or a for loop. And one of the things you'll quickly realize is that for a lot of recursive problems, you actually are able to rewrite it in a more traditional for loop or a while loop. And this kind of goes back to this idea that at the end of the day, all these loops, all these kind of principles we're teaching you, and recursion included, they're tools to help you do a job, right? You don't have to use them at every single time, and oftentimes more than one tool will get the job done. It's really a matter of, one, what are you more comfortable with, and two, what is more effective for this specific job or ask. Um, Recursion people. So I guess I think we talked about loops enough. Let's talk about why sometimes we use recursion, or why recursion does have as much popularity as it does. The upsides of recursion are I think two main things. The first one is recursion really tries to break a problem down to the most fundamental level, and this is something that we started doing a little bit yesterday with this idea that, hey, we don't want to write a function that does 10 different things starting on line 1 and ends at line 10, right? Yesterday, we started seeing these examples of us calling functions and getting back values from other places and using those for the values. And really, we're moving to the world where we actually want our functions to be as simple as possible, right? We want a function to just do one thing, and if we need 10 things done, we'll have 10 functions that each do it individually, and then we'll have one function at the end that calls all 10 of those. That's kind of the world we want to move you towards, and that's kind of how programming looks kind of more in the real world. And the reason for that is because a lot of times, if I want to do 10 different things, it helps me to have 10 different functions. Because what if I want to do something else that only does 8 of those 10 things? I don't want to have to rewrite those 8 things, right? But if I have 8 individual functions, I can have one function that calls all 8, and I can have another function that calls those 8 plus 2 more things. And now we grow into a world in which, hey, for every piece of code that I need, I only need to write it once. And for every piece of function or kind of programming that I use, it only does one thing really well. And when I look at it, I know exactly what it does, and I don't need to look at a function and say, okay, this does 10 different things. Let me keep track of all 10 in my head. It's like this function does one thing, and therefore it should be very easy for me to figure out, okay, this does this. Great, I move on to the next one. This does this, etc., etc. So recursion somewhat takes that to like a more defined end, in the sense that when you look at a recursive problem, a recursion problem tends to be kind of, if you read it close enough, you'll see that usually it's pretty direct and succinct. And this problem is only doing this one thing, or over and over and over again. And once you understand what that one thing is, you also understand kind of why recursion is used as often as it is. The other reason why I like recursion, or the other reason why recursion is so common, is because when you use a for loop, usually, not always, but usually, we do a for loop for a set number of times, right? Recursion really has no limit on how many times you can do it, or rather, the limit is being set within the code itself. So in that respect, it's very similar to a while loop. But the reason why recursion is also really powerful is when we talk about the idea of the call stack, you'll see how it can actually branch through. It can branch through the work tree very logically, and all that is saying is that it actually lets you kind of do things, an infinite amount of times, but be able to keep track of all of it in parallel, which is very hard to do with a simple while loop. But let's talk about simple recursion first. Okay. Oh. Okay. So the call stack. The call stack is basically, so when I think about a computer and kind of how a computer runs, right? The call stack, I think the most common analogy that people use is it's like a stack of plates and a buffet line. And what I mean by that is computers, for the most part, like I said, they're very logical, they're very good with directness, they're very bad with ambiguity. And usually, computers try to boil everything down to a binary, right? Is it true or false, yes or no? the minimal amount of ambiguity. When I run a series of commands on a computer is also, because a computer needs to be very logical and very sequential. A computer also can only really ever run one thing at a time, right? And for our purposes, everything that we've done, we've run things one thing at a time, right? When you look at code that goes from line 1 to line 10, it starts at line 1, right? It waits till line 1 finishes, then it goes to line 2. Waits till line 2 finishes, it goes to line 3, right? A lot of that is really crucial for us because we write dependency, right? We assign a variable on line 1, we change the variable on line 2, and then we use the variable on line 3, right? If it doesn't happen in that order, our function breaks down pretty quickly. And so because of that, the computer is also very good at kind of maintaining this idea that, okay, I will work on one thing at a time. I just need you to tell me what my next thing is, what my highest priority is. Where the buffet line example comes in is if you ever do a buffet line, right? The idea is there's a stack of plates, right? And usually if someone has like a new plate, or let's say you wash a plate, and you have a stack of plates kind of face down, after you clean the new plate, where do you put the plate? You put the plate on the top of the stack, right? Similarly, if you're going to get another plate of food and you want to grab a plate, what plate do you grab? The one on top, right? And so this is this idea, it's called LIFO, it's default, it's called last and first out. It's this idea that really how a computer recognizes commands is the latest thing you give it becomes its priority at that time, right? So when I execute 10 lines of code sequentially, what's happening is I'm giving a computer the code from line 1. The computer says, all right, everyone hold off. Let me finish this execution on line 1, and then I'll wipe that off, and then give me line 2, right? All right, everyone hold off. Let me execute line 2. Okay, I'm done with that. All right, let me clear it off. Let's go to line 3, right? So a computer at any given moment can only handle one command at a time. Okay, so that's a simple idea of a call stack. And so when we build up a call stack, it can get. There's a variety of ways to do it, but for the most part, when people add something to the call stack, it means this function is being run, or this piece of code is being run, and it hasn't yet finished. And as soon as that function finishes, we wipe it off the call stack. And so far, we haven't dealt with very heavily stack calls. What I mean by that is usually when we write our solutions, it's usually just kind of one function that runs all the way through, right? This function goes from line 1, sequentially down to the bottom, and we finish. And so in that case, our call stack is actually very shallow. There's only one function running at a time. With recursion, given how we define it as a function that calls itself, we'll see how this call stack kind of gets very, very messy very, very quickly. Right. Okay. So in this example here, how JavaScript actually can treat this, right? If we imagine this line as like our table or our computer baseline, or I guess like the placeholder at the buffet line, when a computer reads through this code, right? Remember I said yesterday, lines 5 through 7, we're just creating a variable. We don't know if that will be used, and so as of right now, the computer doesn't actually care too much about it when it's running the code, right? The first one goes through. Okay. So lines 5 through 7, okay, I'm creating a variable, not sure if I'll use it, whatever. Line 9 through 11, same thing, I'm creating a variable, not sure if I use it. Line 13, this is really the first line on the page in which we're actually running code, right? We're actually executing code, we're actually running something. I know this because of the open and close parentheses after the first function. So to a computer, the first thing it'll do is this, it'll say, okay, great. This is my first plate, this is my first part of my call stack. It's hard to write in this angle, but this is first, right? This is the first function. Right? Let me add the open and close parentheses. I'm going to execute the first function. Can you see how they were? No? All right, I'll draw it higher. I'll draw it higher and smaller then. All right, up here, this is the call stack. Good? All right, the first plate is going to be, it's easier for me to actually, it's first. Okay? Now, remember what I said, right? Computers only want to execute one thing at a time. So before we even look at line 14 and try to figure out what second is, computers will say, all right, before I touch second, I actually need to resolve first, right? I can't move on to the next line of code without resolving my current one that I'm on right now. This is my highest priority. I need to finish this first. So then at this point, I will say, okay, great, let me execute first. What does first do? First console logs out I am first. So if this is our console log, it will do is it will actually console log out I am first. Okay. Are we done after we console log out I am first? Or is there more to do? In the first function.
It returns undefined.
Yes, it does return undefined, but here notice how we're not capturing anything.
Oh.
So what is returned? It is returning undefined, but we just kind of like let it go into the void. We're not capturing the value anywhere. So in terms of kind of running code, we can say that the first function is finished, right? This first function is finished, and now we take it off our call stack, and our call stack is now empty. Turns out, okay, great. You gave me a command on line 13 called this first function. I ran it successfully. I'm done. Gives me the next command. The next command is going to be second. Okay, great. Everyone hold off. Let me put second on my call stack or my queue. Let me run it. Okay, what does second do? Second goes up and says, and we run the function, and the console logs out, I am second. Computer says, okay, great, that's the end of this function. I don't care about the return value for now because I'm not capturing it anywhere. I finished running I am second. Let me take it off my call stack. I've now finished that function. Is there any more code to run? No, there's not. So at this point, the computer says, okay, I'm done. Right? This is the very basics of how a call stack works. We just go through it line by line, and we don't move on to the next line until we finish the line that we're currently on. Okay. So let's look at this example here. Once again, lines 1 through 5 and 7 through 9, I don't care about my first read through it because there's variables being created, right? Line 11 is the first time I'm actually running code. And in fact, the function is called first. So I know at the very least I'm going to run first. Okay. So now, what is mostly facing me? I told you guys can see. Okay. Okay. So I'm running the first function, right? Okay. What does first do? The first thing first does, if I go through the function now on line, that starts on line 1. On line 2, it makes me console log out I am first. Okay, great. I am first. Then it runs second, right? And now here's where we can see our call stack actually build up now. Because guess what? We can't wipe off first, right? Because we're not done with first yet. There's a lot more we need to run. It's, we need to run line 4 and line 3, or line 3 then line 4, right? But in order to finish running first, what does line 3 say we have to do? We have to run second, right? And not just run second, we have to finish second, right? We can, remember, JavaScript is going to run sequentially. We ran line 2, great. We only ran line 3 after we finished line 2. And therefore, we can't run line 4 until we finish line 3. And line 3 says, hey, can you call this other function? And so now we actually add something else to our call stack, and it's called second. Okay. If you want to be really precise, I actually should have put console log up here too, right? Because when I run first, I run a console log, and I finish it. I quote unquote finish. I logged it out, and I wiped it off. The next thing that I do is I run second, and it's having me invoke the second function. So what does the second function do? It console logs out I am second. Okay, great. So when I run it, I'm going to run I am second. And then am I done running the second function? Yeah, I'm done, right? On line 7 through 9, it's just one line. It's just console log out second. So now that I'm done with second, I can actually wipe second off. Right? My call stack is now going back to just first. Because the computer realized, hey, I kind of took this detour to run the second function, but that was in order to finish the first function, right? So now that I'm done running second, let me go back to where I had left off in my first function, which was line 3. I finished it. I now go to line 4, and on line 4, I write first is finished. And then once line 4 finishes, I am now also done with my first function. So then what I can do is I say, okay, great, the first function is complete. Let me wipe it off. I now have a blank slate. Great, let's run. So, and then after I finish this first function, it really means I finally finished line 11. And then I check and see there's no other code running. So I say, okay, I'm done running this block of code. Cool. So today we do the problems. Definitely, like, feel free to draw a recall stack if you're in a situation where you get confused. It actually helps a lot visually, especially when you're first learning recursion, to kind of understand like where you are and where the computer is in terms of executing the code. Okay. So this is just a for loop that hopefully everyone's really comfortable with now. That prints out the numbers 5 through 1 in reverse order. And basically we're basically going to write that with a we're basically going to run that, but we're going to run it. We're going to try to rewrite that with recursion, so we kind of see how it works at a high level, right? So once again, right, there's a lot of ways to do this problem, right? The for loop is one solution. Another solution is, hey, you can just manually have a function that logs something out and just call it 5 times. And we'll manually tell it what number to put in each time, right? This is a perfectly valid solution in that it also works. But one thing we'll notice, when we call it out manually is we see a pretty quick pattern, right? Each time we call this countdown function, the number gets smaller and smaller until eventually, we stop at some point, right? But the fact that the numbers are changing very consistently, as we're subtracting 1, means that there probably is an easier way to do this programmatically. And so here we have this function. If you remember earlier, right? Remember on the last slide, the function was just countdown. I give it num and a console log out the num, right? Here, what we're doing is we're actually adding one more line, and this line says, "Hey, countdown num minus 1." And you notice that this countdown is a reference to this function, right? This is what we mean when we say recursion looks like a function calling itself. In this function, we're also calling the countdown function. So let's walk through how this will actually run in real life, in real time. All right, so I go through this page. Where's the first line in which we're actually running code on this page? 12. Line 12, right? Everything else is just defining variables using every I use. Line 12 is the first time that we actually say, hey, actually run this code. Okay, great. So on line 12, it says countdown 5. So as far if I have a computer, I always call it CCD to make it short. Right? If I have a computer, I know for a fact when I hit line 12, I need to resolve this countdown function. I'm passing in an argument of 5. Okay, great. So let's go to countdown and see where it starts. So on line 7, 5 is num. What's the first thing that I do when I try to resolve countdown 5? Rather, what line do I first kind of take action? And what do I do on line 8? Right. I console log out num, which is just 5. Okay? That's me on line 8. Okay? And then now we have line 9. What is line 9 telling me to do? Yeah, Leo? So count down with what? Right. Okay, so let me just be super kind of, and hopefully clear here, right? When I initially call the countdown 5 on line 12, I start my countdown 5. The first thing it has to do is console.log out num, right? So let me just write a little task here that says console log 5. I'll console log out 5, and then I'll wipe this off, right? Because that's how a computer's going to do it, right? It's going to go through and it's going to line by line execute code, and every line of code that a computer executes to itself, it technically is, it's a priority, right? Otherwise, you wouldn't be doing it at this moment. So it console logged out 5, we console log out 5, then we wipe the task off, and now we're still trying to figure out how to finish countdown of 5. So we finished line 8, we're on line 9 now, and line 9 is telling us, hey, now can you do countdown of 4? Okay? Alright, so now let's do countdown of 4. Now we see why this is built on top of this, right? Because countdown of 5 cannot finish until countdown of 4 finishes. Ever see that, right? This is why if I run code just from top down, each task is just one thing. I do it, I wipe it off. I put it on, I do it, I wipe it off. But with this function, I can't just wipe it off because I have to call several other things in order to finish my quote-unquote base task, which is countdown 5, right? I have to finish countdown 4 before I can finish countdown 5. Okay? So if I do run countdown 4, what's going to happen? Well, let's do it. Countdown 4, right? If num was 4, on line 8 there, I'm essentially having a small task that says log out 4. So I do. And then what does that make me do then afterwards?
Countdown 3.
Countdown 3, right? If I try to run countdown with 4 as num, the first thing I'll do is I'll log out 4, and then I'll say, hey, let's run countdown of 4 minus 1, which is countdown of 3. Hopefully you start to see the pattern now, right? If I run countdown 3, what will happen if num was 3? Well, the first thing I do is on line 8, I will log out 3, and then I would do countdown of what? Countdown 2, right? And if you notice with our code, like, when will this stop?
Never.
This will never stop, right? Because even when I hit 0, what's 0 minus 1? Negative 1. Is that a number? Yeah. Well, let's just keep going, right? Nothing to stop it. And we'll talk about that in a little bit. But I guess, you folks see, right? Like, even though we're trying to figure out countdown 2 and then countdown 1 and countdown 0 eventually, right? The goal here is to finish countdown 5, right? Recursion basically says, hey, you can't finish countdown 5 until you finish countdown 4. And then countdown 4 is saying, well, you can't finish me until you finish countdown 3, and then so on and so on, right? So every function is dependent on another call. And so even if we're doing countdown of negative 1,000,000, the goal is still to finish what at the end of the day? Countdown 5, right? And so this is how our plate's built up, is that in a particular function, it keeps calling other functions, and then those other functions keep calling other functions. And so that's how that stack builds up. Okay. And then we'll see, rather unfortunately, that this will go infinitely. And if you do it in most computers, it will probably cut you off after a certain point. It may not be negative 10, it might be like negative like 100,000, but like at some point the computer will say, okay, this feels like you probably had an error. You probably didn't mean to do that. And so when we talk about a while loop, one of the things we say is, hey, you need to basically always be moving towards a future world in which you stop the while loop. With a recursive loop, that's even more important, or I guess as important. And in recursion, we call it the base case, right? So when do we stop doing this? When do we stop doing the recursion? And every recursive function needs a base case, because if there's no base case, the recursive loop will never stop, and you'll never kind of finish the execution, and your computer will either stop running the code or you get something bad back. But hopefully this illustrates why, as important as it is to know kind of when to start and when to keep going, you also need to be very, very careful about when to stop. And so writing the base case is actually one of the first things that we kind of typically advocate people to do when they're learning recursion, is this idea that, like, okay, if I look at your function and you're doing your recursive function, I need to know right away, when are we stopping? And really, are we ever going to hit there, right? Is there a viable path to stopping this recursive function? So now if we look at this code, everything else this code is actually pretty much still identical to our code, except we introduce this if-else clause, right? If num is less than 1, we console log out, done, and we're done, right? If num is bigger than 1, then we do our old code from before, right? We console log out the number, and then we recursively call it with countdown num minus 1. So if we just go here and try to finish our code now, let's just take it for granted that for 5, 4, 3, and 2, we're going to run this code the same way, right? Because 5, 4, 3, and 2 are both larger than 1, right? So 5, 4, 3, and 2 are both larger than 1. So if we had called countdown of 5, actually, I'm just going to restart it from the beginning. It's just not have to deal with any confusion with. Okay, so we do a countdown of 3, right? That's the first time we run code. So here I can have a function that says, okay, CD of 3. All right, great. Num is 3. Let's go through this countdown function starting on line 1, right? On line 3, is num less than 1? No, 3 is bigger than 1. 3 is num less than 1. So let's go to the else. What does the else do? The first thing the else does is says, hey, can you log out the number? Will do. And the second thing it says is, oh, okay, and now also call countdown of what? I'm sorry? Anyone?
2.
2, great. Countdown of 2. So that's a summary. Okay, countdown of 2, right? Great, let's finish countdown 2 then. Countdown 2, num is 2. Is 2 less than 1? No, it's not. So we go back to the else clause. The first thing you do is we console log out 2. And the next thing we do is we run countdown of 2 minus 1, which is this countdown of 1. So let's do one more here. Countdown of 1. Okay. What does countdown of 1 have you do? Is 1 less than 1? No. Okay, great. So let's go to the else clause again. On console log, we're gonna log out 1, and then we're gonna go countdown of 1 minus countdown. We're gonna call 1 minus 1, which is 0, right? So we're running countdown of 0. So now we're at countdown of 0. And then if we run through this countdown function again, on line 3, is 0 less than 1? Yes, it is. Great. And so if it's less than 1, what do? We log out done. Okay. And here's where and then here's kind of where the power of recursion kind of takes, or it's really kind of visually effective. Right? It's like realize that we had this huge call stack, right? Where we're calling countdown 3, which means call countdown 2, and then 1, and then 0. When we run countdown 0, we finished it, right? On line 4 there, we do console.logout done. And then what else is there to run in the countdown function for countdown of 0? Jillian, what else do we have to run in countdown for countdown 0 after we log out the done? We're done, right? So now what I can do is I can actually take this task off of our call stack because we finished it, right? Like we resolved it. There's nothing else to do. I ran all the code that there is possibly to run for countdown 0. So I take this off. And if I'm a computer, I say, okay, great, I finished this call stack, or I finished the top item on my call. What's the next top item on my call stack? Countdown of 1. Okay, cool. So where did I lead off on countdown of 1?
The else statement.
I'm sorry?
In the else statement.
Great, in the else statement. And which line?
9.
Right, because I had to do countdown 0, right? Countdown 1 required to do countdown 0. Well, countdown 0 is finished. So what else do I need to do to finish off countdown 1? Nothing, right? I finished the else. There's no other code between lines 10 and 11. So I'm actually now also done with countdown of 1. And if I'm a computer, I say, okay, great. Now all I have to do is finish countdown of 2 now. Okay, great. Countdown 2. Where did I leave off on countdown 2? Well, I mean, it's pattern hopefully is clear now, right? I left off at countdown 2 required that I run countdown 1. Well, you just saw me finish countdown 1, right? And there's no other code to run for countdown 2. So I actually take countdown 2 off my to-do list on my call stack as well. And then lastly, I started off saying, hey, let's run countdown 3. Well, countdown 3 was depending on me to run countdown 2. And I just finished countdown 2. And there's nothing else I need to run for countdown 3. And so countdown 3 is also finished. And now my call stack is clear. There's nothing after line 13 I need to run. So as a computer, I'm really happy because I finished all of my tasks in this sequential order. Cool. Makes sense? Visually? Yes? It always does when you see it on a whiteboard or a slide, and then when you try to do it, it gets hairy real fast. Cool. So yeah, so the two big takeaways here, right? The base case. What was our base case in the last countdown example? Leo? Yeah, we basically like our base case says, okay, if num is less than 1, you just console log out done. You don't need to call anything else. Like you're finished. That's it, right? That's a base case. A base case is you can also think of it as, hey, if a recursive function is a function calling itself over and over again, when do we not want to call ourselves? And that's the base case, right? So when you write a recursive loop, when we do any workshop together or when I walk over and look at your problems, I always ask you like, what's your base case here? And like, have you thought it through to the point where you understand kind of what you're trying to do? And then the secondly is you obviously want to eventually hit your base case. And so in our case, we kept calling num minus 1, and we knew eventually we were going to hit num is less than 1. But you also kind of like a while loop. You want to be sure that every time you run this loop, you're getting closer and closer to the scenario in which your base case is actually going to be met. Cool. So yeah, so this is the summary of this slide is to tell you that, hey, when you're first testing out recursive loops, test with a small input. We could have tested an for example, with countdown of 1,000, but I probably would have never finished walking through the example if we did, right? So with recursion, it's very powerful, but usually you can kind of test out the basics, including your base case, by using smaller inputs for faster iteration and testing. Okay, so this is another problem that we'll look at together, and this lends itself very well to this idea. This lends itself very well to the recursion paradigm. So factorial, right? If I say, give me 5 factorial, just kind of a quick math refresh. This is what factorial means, right? 0 factorial is 1, 1 factorial is 1, and then from there on off, any numbers factorial is basically just the product of all the numbers between itself and 1, right? So 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1, etc. So we're going to try to build this out with recursion. Okay, so this is hopefully like when you start building out recursive functions, this will hopefully be the first step that you take, right? Because remember, what's like the first thing you want to do in a recursive function? I'm sorry?
Base case.
Make your base case, right? Okay, it's easy for me to call a function over and over again, right? Just call it a function. But let's figure out when I stop. And so if we notice on the previous slide when we did the review of recursion, right? It looks like, we're going to assume just for the argument that like -1 factorial doesn't exist, right? We kind of stop at 0. And 0 is 1, and then 6, and then 1 is 1, and then everything else kind of makes a lot more logical sense, right? It's just the number multiplied by everything between itself and 1. So 0 and 1 seems to be kind of like the places where we stop. We can obviously test the hypothesis later on if we want to, but for now, when we start writing down this example, for the sake of argument, let's just say that if num is 0 or num is 1, we return 1, right? We could just do if num equals 0, we return 1, but we'll see why that can cause some traps down the road. Okay. One thing you also don't want to do is, we could just theoretically just hard code this forever, right? If num equals 0 or 1, return 1. If num equals 2, return 2. If num equals 3, return 6, right? And at some point, we're just kind of hard coding all the values. We do want the recursive function to take place. So usually when you write a base case, the idea is kind of like, what's the scenario either that you definitely want a hard stop, or what's the scenario in which the logic kind of breaks and we're kind of going into our own kind of custom design, right? Custom design as in like, it's not something that we would expect to see if we were to follow the recursive function, if we were to follow it indefinitely. Okay, so now very, very easily, right? Factorial of 0, well, num is 0, return 1. Factorial 1 also returns 1, right? So hopefully that's a pretty strong base case. Okay, so now we've covered our base case of 0 and 1. And then one thing you'll notice with factorial is every number's factorial is equal to what? It's equal to that number multiplied by the factorial of that number minus 1, right? Because remember, 4 factorial is 4 times 3 times 2 times 1, which is the same as 4 multiplied by 3 times 2 times 1. And then 3 times 2 times 1 is just 3 factorial, right? So therefore, 4 factorial is just 4 multiplied by factorial of 3, or 3 factorial. Cool? You good at math? Okay, great. So if everyone is good with that math, then we can kind of see, just based on this, like we can see the outline of a potential recursive function. So I'm going to skip through a lot of this. Okay. Okay. So here, we're doing a console log because we want to show it to you, but eventually we'll get rid of that because once again, console logs don't really do too much. We know that eventually we want to find the factorial of this number minus 1, right? Because if I'm going to calculate out 4 factorial, and I say, hey, by the way, 3 factorial is 6, then all I have to do is like, all right, great, then multiply that by 4, and I'm done, right? So at some point, I actually need to figure out what factorial of num minus 1 is. And if I'm at 2, and I say, hey, what's the factorial of 1? Well, that's going to give me 1. And if I'm at 1, what's the factorial of 0? Well, it's going to give me back 1. Everything else kind of follows a very consistent mathematical logic. So when I do factorial of 2, I get back, or the console log tells me, hey, factorial of 2 is going to be, or sorry, factorial of 1 is going to be 1. So then lastly, if we actually do follow through with our logic of, hey, if the factorial of a number is just that number multiplied by the factorial of a number 1 less than itself, then we can write that on line 8 there. And then, like I said, console logs do nothing for us, right? Return is kind of where the important thing is. And if we return our result, we're eventually going to get back to the answer. So that was not a good explanation of or that was a good explanation of how the code functions, but I think it really helps folks usually just to see this kind of really explain out in painful detail, right? Okay, so bigger call stack for more things. Okay, let's call factorial of 4. Okay, that's the line of code here that I really want to, and I'll call it FAC 4. Okay, that's what I want to run. Given that's my factorial function, and I want to run factorial of 4, right? How do I figure out what factorial of 4 is? Well, the first thing I'll actually do is I'll actually just need to run factorial of 4, right? I call factorial and I pass in an argument of 4, so therefore num is 4. Okay, is num equal to 0 or equal to 1? Sunday morning, the louder you are, the faster this goes. Okay, so it's not, so clearly num is 4, right? It's not 0 or 1, so I skip the if statement. Then on line 8, I move on to line 8, which is the next line. It says, okay, create this variable called result. Okay, and the value is num multiplied by factorial of num minus 1. Well, if I just replace num as 4, then that becomes result equals 4 multiplied by factorial of 3. Okay? In order for me to figure out what, and remember, I can't move on from line 8 until I finish it, right? I have to finish line 8 because I'm running this code in sequence. How do I finish line 8? Well, line 8 basically says, hey, result is equal to 4 multiplied by factorial of 3, right? I need to resolve 4 multiplied by factorial of 3 before I can move on with my code. Great. So what does that look like it's telling me to do then? Like, what's the next step there, Jillian? Exactly. It's making me call factorial again, except now I'm passing in 3 as a number. Okay, let's do it. Is 3 equal to 0 or 1? No. It's not. Thank you. It's not. So we skip on. So we skip lines 3 through 5, and then we hit line 8. And line 8 is saying once again, hey, you need to figure out what result is. Let's figure it out. Well, this variable called result is going to be 3 multiplied by factorial of what? Factorial of 2, right? So in order to move on, so here I'll just write, in order to figure out this, we need to, so this is going to be factorial of 3, and this is going to be factorial of 4, right? As in kind of where we are in the execution, right? This line is used to resolve factorial of 4, right? 3 multiplied by factorial of 2 is what we need to finish off resolving factorial of 3. Everyone good so far? Right? Okay, great. What's factorial of 2? Let's run our thing again. It's not 2 is not 0 or 1, so we skip down to line 8. And now we're just telling I need to figure out this variable called result, and it's equal to 2 multiplied by a factorial of 1. And I need to, the reason I need to resolve is that I need to figure out what factorial of 2 is. Okay? Factorial of 1. What's factorial of 1? 1. Right. If statement, I return 1. Remember, return breaks out of your function scope, right? It is in return returns out the factorial. And so factorial of 1 is going to give me back what? 1. Okay? Now, super important, especially given what we talked about yesterday. It returns 1, right? It doesn't console log it, because console log does nothing. Okay? It returns 1. And why is it so important that it returns 1? It ends the execution of the function, exactly. Why else is it super important that it returns 1? Nancy? Exactly. Factorial of 2 says, hey, I need to figure out what 2 multiplied by factorial of 1 is. If factorial of 1 doesn't return a number, I can't finish factorial of 2. Factorial of 1 has to return. It has to give me back a number that I can use, because there's another function that is explicitly waiting on whatever this function returns. Right? If you console log it, it does nothing, right? So if I see a lot of console logs here, you're wondering, hey, this recursion isn't working, I'll ask you, what is your function actually giving back to the person or the function who called it, right? Factorial 1 is only important because I need to know what it returns, so I can plug it into 2 multiplied by whatever factorial of 1 returns. And if factorial 1 doesn't return anything, then my function is dead, right? So if I say that factorial of 1 is going to return 1, the return basically just means I'm done with this function. I don't need to look at any other code. It doesn't matter to me anymore. So factorial of 1 returns 1. I can actually now go back, so I can wipe this off and say, okay, I got back a number 1. And now I can replace earlier where I had factorial 1. I can now replace it with just a simple 1. Okay? And now I can actually go back and try to finish my factorial 2. Where did I leave off on factorial 2? I left off with 2 multiplied by factorial of 1. Well, if factorial is 1, then what's result going to be? 2. Right? This is 2 times 1. And then what do we do to finish factorial of 2? Right, we return 2, which is 2, right? We return 2. And why do we need to return 2? Super critical, because factorial 3 says, hey, I need to know what factorial 2 returns, so I can use it to multiply by 3, right? If I don't return that 2, my factorial 3 function is going to die, right? So this is why return is super, super critical, because the return value is actually what's going to get used, right? You can console log out every single number you want, but JavaScript says, hey, I don't care what you console log out, I just need to know what this function returns, and that's what I'm going to be using to do my math in the next stage, right? So factorial of 2 becomes just now 2. And so I can wipe this off because I've now finished factorial of 2, and I can replace factorial of 2 with just 2. Okay, great. We now say, where do we leave off our stack? Well, we left off at factorial of 3. And where did we leave off? We left off on line 8, where we said, hey, result is going to be 3 multiplied by factorial of 2. Well, we know that factorial of 2 is 2, so result is going to be what? 6, right? So on line 8, we've now figured out result is 6. So we went on line 9, and we returned the 6, and we're done with the function, right? Returning the 6, once again, super critical. Why? Because we started this whole process off by trying to figure out factorial 4. And we said factorial 4 is just 4 multiplied by factorial 3. Well, we just figured out what factorial 3 is, right? It's 6. So if I replace this with 6 now, in factorial 4, let result equals 6 or 4 times 6, which is 24. And then I return the result. I return 24, and assuming I called factorial 4, I return 24 to the page or to the global scope, or whatever you're going to call it. And then, if that's the only line of code that I'm running, then I'm actually done with that code at that point, right? There's nothing else to run. I returned everything I needed to return, and there's nothing else I need to do. And so I finished factorial 4. I return 24 to the page. We'll say that's a return. And now I'm done with code. So that's like a walkthrough step by step of how a recursive function works, right? At every stage, you need to figure out whether or not you want to call yourself again, and then also what you're expecting to get back from the call, right? If your recursive function doesn't return anything, more likely than not, you're probably doing something wrong. Because the whole point of using recursion is to use a function to calculate something so you can use that value for a later purpose, right? If your function doesn't return anything, that means it's not giving back anything useful to the person who called it, which kind of begs the question: why call it in the first place? Okay. Any questions on that example of factorial? Does this make sense in context of doing the pre-reading from last night, like why this works and kind of how we're stepping through this? Okay. Okay. I literally think everything else on this slide is just another animation of kind of what we talked about. Cool. So 3 things, right? Once again, always define your base case. Test it with very simple values first because that's just gonna make your code a lot easier to run. And then as you get more and more comfortable with your code running well on like kind of simple inputs, then you can run more and more complex inputs. This is just to let you know that a lot of times, especially when you first start off learning recursion, you might think, oh, I can do a lot of this with a for loop, with a while loop, or something else. And the answer is yes, you can. For the purposes of this workshop and these problems, use recursion. Don't use a for loop. And it's just because we want you to practice recursion, right? There's no point in doing these problems with for loops because it kind of defeats the purpose of trying to learn a new concept. Yeah, so 3, or rather 2 most important things, right? Start with your base case, and then be able to test out your base case with simple inputs. Cannot stress that enough in terms of like the processes for getting off the ground. And also return statements, super important, right? You should almost always return something from a recursive function because if you don't give back a meaningful value, there's really no reason to use that function in the first place. Any questions? Cool. All right, let's get started with workshop then.